My name's Sanjif. I'm joined here with a teacher as well, and we're here representing Groq. Today, we're going to introduce Groq, talk about what we do, and hey, hopefully by the end of this, we would have convinced you to use Groq for your hackathon and hopefully beyond as well. So, what do we do at Groq? At Groq, we build and deploy custom ASICs. We call them LPUs, and this is short for language processing units, which we use to be able to run AI and also HPC inference workloads at low latency in a manner which is deterministic and also in real time. Now, as the name suggests, LPU, language processing unit, we're focused on language and in particular LLMs. And the claim here is we run LLMs at the fastest inference out there. Now, it's a pretty big claim, but I think I'm going to substantiate this with some examples. So you can also follow along as well. I'm going to head on down to www.groq.com. And if you don't see this screen, you might need to sign in with your Google account. But once you do that, you'll be presented with our UI. And on the right-hand column, you can select all the different LLMs we have out there. So as you can see, we have these open source LLMs, Gemma from Google, Llama from Meta, and also Mixtral from Mistral. We don't train, we don't fine tune these models, but what we do is we port and compile these models into our LPUs, and we're running them right now in our data centers in Washington. So let's go ahead and choose one. I like Llama, and we can prompt a question. So maybe I can ask, tell me more about University of Michigan. All right. So the first thing to note is that was pretty quick. And the reason for that is because of our hardware and also our software stack on top of it. And if we look at this kind of token per second quote in the top right, we can get a more detailed breakdown of what's going on under the hood. So we can talk about input tokens, how fast we process that, and also output tokens. So 1,260 tokens per second, that's pretty quick. But everything's relative. So how fast is this really? And for that, I go on to the next tab. This is a third-party benchmark by artificial analysis.here. And over here, they have all these different API providers, and it kind of gives us these quadrants of price versus output speed. And if you can look over here, Groq is comfortably in this top left quadrant where we are the cheapest and also the fastest. So there we go. I think I've substantiated that claim well enough.
And just to add to that, I think they had to create a whole new quadrant. So to put us in our own league there on the benchmark, which is fun fact.
Thanks, TJ. Yeah, that's pretty cool. But yeah, now that we've proven that, I guess the question is, why do we care about low latency inference? Why do we care about real time? Why do we care about determinism? And maybe I can talk a little bit about inference. If we look at the landscape of machine learning, I think the bulk of it in the past is comprised of training. But with the emergence of these kind of foundational models, these generative models, we're moving slowly into a regime where you train once and then you run multiple runs of inference in production. So the bulk of your compute is going to be on the inference side in production. So that's why we care about inference. And in terms of low latency, well, for example, in the case of LLMs, we get a response in real time. This allows us to talk and also get a response and also iterate upon our responses and prompts in real time. So that's crucial. All right, so now that we care about low latency inference, in particular about LLMs, and we've shown that Groq can do this very, very fast, I guess the question is naturally, how do we do this? And in part, this is due to the hardware and also the software. But let's begin with the hardware. And before I can even talk about the hardware, I think we need to talk about LLMs in general, because to accelerate something, we need to kind of understand how it works in the first place. And my understanding of LLMs is they're composed of these stacks of decoders. And if you kind of dive deeper into these decoders, they kind of comprise of large matrix multiplies and also element-wise operations for these non-linear kernels at the end, the activations. I forgot the name. So we want a hardware, we want some kind of system which is able to run these large matrix multiplications and also these vector units, this element-wise additions, multiplication, so on and so forth, in a way which is really efficient. And we have that over here with the Groq chip architecture. So if you have a look in the middle, that's the architecture of the Groq chip. And for the more studious among you, you might notice that it's symmetric along a vertical axis. So you can kind of fold it in half. It's going to be symmetrical. And on the innermost column, we have the vector units. These things handle things like element-wise addition. It's sandwiched by layers of SRAM. So these are the memory slices. And on right outside, we have these switch execution models, and these do transposes, it does shifts, so on and so forth. And most importantly, on the outer ends of these two hemispheres, we have the matrix multiply units. We call them MXMs. And these really are the workhorse of the chip. It does the bulk of the matrix multipliers, which are the bulk of machine learning and also HPC workloads. Right. So let's talk about how all of these different components help LLMs. LLMs by nature and also by name are very large. So we need a lot of memory to store them. We have SRAM on chip. We don't really play around with, let's say, DRAM or anything like that. All of the memory accesses happen on chip. And this helps us a lot because we don't have things like cache misses. Everything is laid out on the chip, and the compiler knows deterministically at each given cycle where each memory element is. And because of this, it can kind of push the data along from functional slice to functional slice as it gets processed before saving in memory. So one, it prevents all these cache misses. And number two, it allows you to move data as you process it without having these unnecessary reads and writes in between them. And if you look at the statistics of the SRAM per chip, it gives you 80 terabytes of bandwidth. That's pretty large, and it's significantly higher than HBM. But we have a little bit of a constraint here, which is the capacity per chip. So LLMs, you might have 70 billion parameters, maybe even more than that. And that takes gigabytes of memory. Per chip, we have about 220 megabytes of SRAM capacity. And because of this, we need to network out into multiple other chips. And the regime we do this in is, it's called tensor parallel. So for example, if we have a kernel, a matrix multiply kernel, which doesn't fit a single chip, we shard this across multiple chips in nodes, across nodes, and also across racks. And we pool the memory to be able to maintain this 80 terabytes per second of bandwidth. Of course, we are bottlenecked by the bandwidth of networking, but in practice, we still get very, very good results. All right, so those handle the matrix memory operations. We have the matrix multiply units, and we also have the vector units in the middle, which handle the element-wise operations. Something we haven't talked about yet is Groq true point. So when we think about AI in particular, data formats are very important. People use FP4, FP8, FP16, int8 for quantization. We have a feature called true point, which allows you to do these float 16 matrix multiplies while still maintaining accuracy. The way we do this is we do an accumulation in a higher bit register, and then we reduce it down to float 32. And in practice, this does help improve our performance in terms of accuracy. All right, so I hope I've convinced you that we have an architecture which is suited for LLMs, but like I mentioned before, LLMs are comprised of, sorry, did anyone? Oh no, that's fine. Like I mentioned before, LLMs are comprised of large matrix multipliers and also vector units. This generalizes to machine learning and, in general, most machine learning models, convolution models, transformers, GNNs, you have these matrix multipliers and you also have vector operations. So in practice, in theory, I guess, this chip should do well and generalize not just for LLMs, but also for other machine learning models. And for that, I'm going to take you to this ML agility page where we benchmark. Sorry.
Quick question there about precision. So you're doing FP16 and NVIDIA simulations in 32. Do you also support like other lower precisions, like you can maybe just giving this like a BF16 or a FP8, BF8?
So we don't support BF16, and the way we support FP8 is with the FP16 kernels. So we do the FP8 operations with the FP16 kernels, we just zero out the corresponding bits. Yeah. And in practice, that helps us a little bit with the memory footprint, but we're still using the float 16 kind of units.
For the arithmetic, for the actual like operations, but not necessarily for the memory. Okay.
Yeah. Okay, I hope that answers that question over there. And over here, we have a list of all the data types supported. So ints, floats, and also Booleans. But what I was talking about before was how this chip also performs extremely well. The LPU performs extremely well across other machine learning models in general. And to that extent, we've worked on this open source benchmarking tool called MLagility. And we use our tool called Groq. I'll talk about this a bit later. But we pass in models online, all these open source models, and we benchmark them against the CPU, against the GPU, in this case it's the A100, and also against Groq. And you can kind of see how well we do across, I want to say about 168 odd models taken from Torch Hub. So these are CNNs, transformers, Hugging Face, mostly NLP type workloads, so transformers, Torch Vision, CNNs, and we do particularly well. So if I choose the baseline to be the GPU, we do significantly better. I think this is skewed because of some workloads, but the point stands, we do particularly well. And if you have a look at the data points below here, you can see all the different models we've ported and the performance you get. And in a second, I'm going to talk about how we can actually interface with Groq to port these models yourselves. And I think the hands-on session later on today is going to give you a kind of step-by-step workflow of that. So let's go back. We can scale from Groq chip to Groq card to Groq rack. And we can port this with our Groqware suite. I think I'm running a bit out of time, but we did start late, so that's okay. So I mentioned half of the story, which was the hardware. And now the second half is the software suite on top of that. And that's what we call the Groqware suite. So from an applications engineer point of view, we want to be able to get our machine learning model compiled and also running on whatever hardware we want. In this case, it's Groq, the Groq LPUs. Let's kind of walk through step by step how we'd end up doing this. So let's say we have a PyTorch model. It could very well be a TensorFlow, Keras, or Onyx model. What we do is we convert this into Onyx, which is a form of intermediate representation. Onyx stands for Open Neural Network Exchange, and it works to kind of allow interoperability between different frameworks. PyTorch has a lot of operations, TensorFlow has a lot of operations, and you really use these to describe the same architectures. And Onyx works to kind of consolidate these and allow you to move from platform to platform. So we have a model, we convert it to Onyx. Onyx then lowers this into Onyx IR, the intermediate representation. And from this, we pass it into our Groq compiler. The Groq compiler is then kind of split up into 3 individual layers, the front end, the middle end, and the back end. In the front end, we convert this into our own IR, we do a translation, and then we partition the model across chips, and then we schedule this in the compiler. Once this happens, it spits out assembly code, human readable assembly, which we then compile into an executable, which we call an IOP, an input-output program. And then once we have this, we have the binary, we combine this with the runtime, and we run inputs on that. Simple enough. Now, it does have quite a few steps you have to go through, and because of this, we've abstracted everything away with Groq. So with Groq, you just pass in a PyTorch input, for example, and it gives you a model which you can pass inputs in and run directly on the Groq chip. And on top of all of this, we also have dev tools. So for example, we have a profiler, which allows you to kind of see how much of the runtime is being used on each individual kernel. It gives you a view of where the data elements are on the chip. I'll show you this in a second. Yeah, there we go. So like I mentioned, this chip is deterministic, and within each cycle, you know exactly where all the elements are within the architecture of the chip. And I'm not entirely sure what application is running on here, but you can see the data moving from functional slice from memory as it kind of gets transformed throughout the process of the application. I talked about Groq Flow a little bit, and I mentioned with the ML Agility benchmarking tool that we use Groq Flow as the main interface. But how do we actually interface the Groq Flow to get something running on a Groq LPU? So it's 3 simple steps. First, we get the model. In this case, we're working with a GPT-2 model. We instantiate it. We create dummy inputs, and we specify them as a dictionary with the name of the inputs, and then example inputs with the data type as well. For those of you familiar with Onyx Runtime, it's a very similar type framework where you pass in a dictionary. And then we call the Groqit API from Groq Flow, and this does all of the steps we mentioned earlier one by one. So it converts to Onyx, it optimizes it, it compiles and it assembles, and then to run it, just unpack the dictionary with the Groq model, and it gives you an output. And if things don't go according to plan, it'll give you clear instructions on how to proceed further. And of course, if you wanted to talk to us or contact us about any issues, we're more than happy to help. So that's Groq Flow. Earlier we talked about the Groq chat kind of user interface. And after this, the teacher's going to talk about how you can interface with the Groq chat API. But for now, that's kind of my section wrapped up. I'm going to stop sharing. If anyone has questions, happy to take them now, maybe later once the teacher's done.
Okay, if there are no questions, thanks, Sanjif. I'll share. And hopefully everybody can see that. Okay. Hi, everyone. So I'm Hatice. And today we're really, to boil it down to a couple words. I don't know how many of you have heard about Groq before. I wish we could kind of see the audience, but the camera is, towards the front of the room. We are trying to show you different ways that you can access the Groq LPU inference engine, the technology that Sanjif just introduced you to. So one way for that is what he showed you via the Groqware suite and Groq Flow, which will be accessible via the Groq rack that we have available at the Argonne Leadership Computing Facility that I believe you will get instructions on how to access later for your hackathon. And the second part of it that I want to introduce you to is the Groq API. So a few months back, we launched our Groq Cloud. So we did this because, as Sanjif mentioned, there is a switch now from training models to inference. And ever since the explosion of LLMs and ChatGPT and the commercialization of these large language models, we wanted to be able to give everybody kind of a taste of the inference speeds that Sanjif showed you. And that's available on benchmarks for world's fastest inference speed very easily via Groq API, so that you're able to use the API and integrate into all of your applications. So with that being said, Sanjif already showed you this, so I'm going to continue on. What Sanjif showed you was Groq Chat, where it's Groq Chat and our corporate site, which is groq.com, where you can create an account or log in and see the inference speeds. But I want to show you a second part of it, and I'll skip these slides. So if you're following along with me right now, and I'm going to go through this process with you, if you have a laptop open in front of you, you can go to console.groq.com. So this is what we call our developer playgrounds. Once you log in, and I will log in here as well, you are welcomed into our developer playground here. So this is going to be your hub for accessing Groq API directly and being able to integrate into whatever apps that you build up. And I will give you a little tour of this. So similar to Groq Chat, the console has a system prompt, you have your user message, and I think they just changed this, actually. This did not look like this yesterday, so if I were to say anything about Groq's speed lately, not just with inference speeds, but the way the team is moving, I think this is a testament to that. We have all of our different models available here. We recently also launched Whisper Large V3. You have some extra parameters that you won't be able to see on Groq Chat that you can play with here. And then you have your documentation to get started. So I'm not going to go, too deep into the weeds here. You will have everything that you need to get started here, and I'll give you some resources that you can work with. But we have our quick start, we have our examples, we have our applications that you can take a look at here as well. I think the main feature that I'll show you here is the API key. So right now, Groq API is in a free beta. And we have, I think I skipped one of the slides, but we now have 295,000 developers on Groq API and using and building hundreds of applications each day. So what you need really is to go to API keys on the console, and then you can just very simply create an API key for free. And then once you do, you'll be able to see all of your rate limits under settings. But just for all of you, we know there's a hackathon that I believe is going to last maybe about a week. I am going to be sharing some additional resources such as Discord, and I know the amazing Argonne team will also be helping with questions. If you reach out to us and you would like increased rate limits for your applications, we can directly bump these up for you. So don't be limited in your creativity due to rate limits here. We can always help you out with that. So you can very easily get started on the console here. And actually, I want to show you a couple applications just to maybe inspire you a little bit today to see what you can build with Groq API and access to the world's fastest inference for real-time applications. Here, this is actually one of my favorites. You can see I've used it quite a bit. This is an application called Concilium. It's actually live. You can use it yourself, concilium.app. It's built by a developer named Philippe. And what it basically does, it uses Groq API and Groq in the back end. It will, in real time, create a lesson plan for you for any topic of your choice after you fill out the parameters here. So here, let's say topic name. I don't know if anybody from the audience has something that they've been dying to learn lately. Anyone? Maybe not.
We're gonna get you an answer.
What was that?
I think one thing that I'm trying to learn is how do we apply scaling laws for chemistry foundation models. Maybe that's a bit pushing it.
Say scaling laws.
Scaling laws. Let's do scaling laws.
Could you make that out, Sanjif? It's a little.
I heard scaling laws.
Scaling laws? Okay. I hope that's correct. I don't know. I know nothing about this, so I wouldn't even be able to give you a goal here, but let's see. I don't know. Is there anything you can add here to goals?
Maybe something like learn about neural networks and how they perform with data set size and model size.
Okay, that's perfect. Thanks.
We had a tutorial on this last week, so we'll see how this this goes.
Okay, perfect. I hope it's accurate, but it's using LLMs, so I think this is using Llama 3 70B in the background. So let's see how it is. Backgrounds. I took an introductory course. I know nothing else. Let's say that. Okay, and then let's generate a study plan. Okay, so here in real time, it's coming up with the outline for the course, and this is This is not in detail just because I didn't add in too much detail to like my goals for the topic, but here you can click into each section. And then this says a bunch of stuff that is hopefully right. I don't know if you can read my screen, but
Yeah. It's cool. It catches power law relationship.
amazing. Implications
Yeah.
for neural network design, model size effects, scaling law of model size, and then here you can go to data set size impacts and etc. Really cool app. I wish I were still in school to use this. Kudos to Philippe who's created this using the Groq API. So that's, you know, one example. Another example, this one is Project Media QA. This was developed by one of our interns on the team. And it basically uses the Whisper model for transcription. I know we're right on time here, so I might not even show this, but
No,
the
no,
example
we can
was-
go a few minutes over it.
That's
It's
good. Okay,
yeah.
perfect. Okay, let's record this then. Hi, I'm currently presenting Groq for a webinar for University of Michigan. Hopefully everyone's having a great time. We're here trying out the different applications that people have built using Groq so that we can get inspired. And then I'll stop recording that. And then let's click transcribe. So, okay, did that work? Do I have my API key? Okay, perfect. So this is pretty accurate. Now, what this application does, it combines two things. It combines Whisper for the transcription of the audio, and then it also combines the other LLM models that we have. So you can actually ask questions about the transcribed data. So I can say, who is the webinar for? And it should say University of Michigan. So that's just another, and then the tokens per second, 1378, which is really insane. You could imagine the implications for real-time applications with that type of speed. But I'm going to jump right back into our presentation. Hopefully that was a fun little inspiring demo session. And I don't want to start from the beginning. Okay. I am not tech or PowerPoint savvy, so we're just going to skip ahead like this. Okay, so console.groq.com, the way that you can access Groq API. We have, to get you started beyond just the documentation that's in there, the Groq API cookbook on GitHub. This includes different tutorials for, let's say, RAG applications, the features that we have, such as JSON mode, streaming, tool use, designed by engineers at Groq and actually external developers from our developer community that you can look into for inspiration and just to learn how to do things. Speaking of developer community, I just want to put a plug in for a Discord server, which is at 17K now. You can use this QR code to join. I'm very active in there and am happy to answer any questions that you may have. So if you join us there, you'll be able to connect with developers all across the globe, as well as see applications and ask any support questions. And then lastly, the hackathon. If you end up building something cool and you want to share with us, we're more than willing, if you reach out to Sanjif, me, or any of the amazing individuals on the A&L team so that we can get in touch. We would love to work with you and showcase your work. That's built on Groq on our website and our blogs. I think that'd be really fun. So there's always this option. And then I'm at the end, but I just need to give one last plug. Speaking of open source, Sanjif showed you ML Agility, Groq Flow. We last night dropped 2 new open source models that are specifically designed for tool use and are now available on Hugging Face. They were built on top of the Llama 3 models by Meta. So they're #1 on the Berkeley function calling leaderboard, ultra fast, ultra accurate. You can see more about it if you join the Discord, and I've made an announcement post that has a full blog, but just wanted to let you all know about that as well. And I know we're over time, but hopefully you were able to learn a little bit more about Groq today, what we offer via the ALCF with on-prem hardware that you can access to play around with Groq Flow, and then also Groq API that you can access via the console, so you can get started building with our API for your applications. All right.
Thank you so much.
Thank you so much for attending. And thanks, Sanjif, and thanks, team. That is all. Hope you all have a great day and good luck with the hackathon.
All right. Thanks a lot. And I think you've taken us to lunch here.
Awesome.
Thanks for that. Very, very excited, and congrats to your team for all the amazing progress.